black to present some main points from this May. We have discussion campaigns with which was instead in of optimality of experimental design in the sense that one corollary is formulated in this step. We are restricted to 10 minutes. We formulate the model. We consider a design D with M blocking factors. So we have the treatment effect denoted by alpha I and M blocking factors. In matrix notation, we may write Y as the sum of U alpha, U is I matrix corresponding to treatment effects, and matrix ZK correspond to block effects. M blocking effects. Because M is 1 in the design, M is 2 in the case of designs, elimination, heterogeneity designs, and so on. As already mentioned, here delta and K and is well known. And then may be represented as CK corresponding to the situation where block factor and the metric matrix which penalty term of induced additional blocking factors. As here we assume that sigma square in the model containing K blocking factors is exactly the same as sigma square in each submodel where the number of blocking factors is reduced. A general remark is that we consider here the situation of when the penalty term Bk vanish, which is of some interest from several points of view. And the main result of our note is the following. We ask when the information matrix for the design, for the complete design containing K blocking factors, is just identical with the information matrix corresponding to a sub-design where only one just K's blocking factor is present, and this is even only if the following equation is satisfied we have nk. K is a fixed blocking factor now. This is incidence matrix between treatment and K's blocking factor. Nk, delta k to minus 1, the inverses of the sizes of blocks for K's blocking factor, and nkl is the incidence matrix between K's and L's blocking factor. This must be equal to the incidence matrix between treatment and the L's blocking factor for each L, which is different than K. The main idea used in the proof is as follows. In matrix notation, C is simply U prime. In the middle term is the projector onto orthocomplement to the column space spanned by several matrices Z1 up to Zm, and we simply use the decomposition of this Q. This Q is identity matrix minus, here we have the projector on the original subspace spanned by Z1, or we fixed without the loss of generality that K is 1. And here we have modified subspaces, this is S2 and Sm. Those who participated in Haruo Yanai's session yesterday afternoon noted that this decomposition is also among his favorite tools. And after some simple algebra we get this condition, which in terms of the incidence matrix may be formulated as before. This condition is just equivalent to what Eccleston and Russell in their 1975 and 1977 biometrica papers called adjusted orthogonality. I think that in this workshop, this term was first time used by Professor John on after Monday afternoon session of block designs. So there's another or alternative term used is strict orthogonality, and relationships between strict orthogonality and weak orthogonality were studied, for instance, in a paper by Kirti and Shah. This is linear algebra and applications. By George Steyer in 1986, this is proceeding of the Pacific Statistical Congress, and so on. Eccleston and Russell predicted that this concept of adjusted orthogonality might be useful and reasonable in many situations, and actually we can agree that this prediction was a very good one. We have 3 corollaries and 1 example. Now we restrict to a 2-way block design, which is just an alternative name for row and column design. And we consider the situation where treatments are orthogonal to rows after adjusting for columns. Then such a design has the same subspace of estimable treatment contrast as the treatment column 1-way block design. Usually, or in general situation, introducing each additional blocking factor may diminish the subspace or the dimension of the subspace of estimable treatment contrast. Here we have the situation that if the adjusted orthogonality property holds, then this subspace remains unchanged. So in particular, if the original design is connected, then this original design or this design with 2 blocking factors is connected even only if D2 is connected. In general, we have the implication that connectedness of D implies connectedness of D2, but not the other way around. Now the corollary which is related to the title of this session. If this property, which is discussed in this paper, holds, then we have an exceptional situation, namely we have the uniform optimality situation which refers to the usual Levner matrix ordering mentioned by the organizer of this session, and the exact formulation of corollary is as follows. We have M-way block design in which treatments are orthogonal to blocking factors L, different from the fixed to each blocking factor L, different from a fixed blocking factor K. Such a design is uniformly optimal for the treatment contrast among the class of all designs with the fixed marginal incidence matrix NK. This is incidence matrix between treatments and the blocking factor K. This is a strengthened version, or in other words, this actually enables to give an interpretation for what Pukelsheim and Titorington called a determining blocking factor K. Namely, they found that if a design has if a factor or blocking factor K is a determining blocking factor, which is defined that just a single level of each blocking factor different than K appears with a level Jk of a factor K, then the design has the property which was mentioned before. Our criterion, or our main theorems, leads to the following interpretation, namely the fact that the design has a blocking factor is equivalent to the fact that the equality C equals Ck holds irrespective of the treatment matrix U. So if this equality C equals Ck holds for all U, then it corresponds to the situation that the K's blocking factor is the determining blocking factor. So this actually shows how much stronger the concept of the determining blocking factor is. What is characterizing theorem 1 is a situation where U is fixed, which is actually the classical situation we have in experimental design. And I will conclude with an example, namely the quite good choice of examples or row and column designs which have the adjusted orthogonality property, and so we consider a two-way block designs with the property that rows and columns are orthogonal after adjusting for treatment. This is this classical situation considered in the literature. Here we have the example taken from a paper of D.A. Anderson and J.N. Ecclestone. This is just our first reference, 1985 JSPI. These numbers here denote treatments. So we have 36 observations, 12 treatments, 4 rows and 9 columns, or in other words, we have 4 times 9 blocking system. If we interchange treatments and columns, and then after appropriate permutation, we get the following example. We have still 36 observations, now on 9 treatments, and the blocking system now is 4 rows and 12 columns. This denotes blanks here. And this design satisfies consequently, because this design had adjusted orthogonality property, so this design satisfies the property which we need, and the conclusion is that according to corollary 2, the design here formed is optimal in this strong sense among all two-way block designs which has the following treatment column incidence matrix.
Thank you. Any questions addressed to the speaker? Yes.
There is a, just draw attention to a paper that's just come out in the Journal of Royal Statistical Society Series B by Professor Dean from Ohio State University and one of her colleagues, I think one of her students, which has virtually the same title. I think it's covering some different things, but you might be interested in seeing where the impact is there.
A recent one.
Yes, it's Series B earlier this year.
Yeah, thank you.
I have a query here. Is it possible to have a situation where a design with given nk with adjusted orthogonality can be improved by another design with different nk and not having adjusted orthogonality? Because within the class with the same nk, of course, this is not beatable.
Yes,
but
of course.
you may have a design with a different nk which does not have adjusted orthogonality with remaining factors but could be better.
Yes, correct.
It would be good to look for example. Of course, it can't happen where nk is the determining factor because then it will be
Yes,
good
yes,
for
that is
that.
impossible.
But
Yes,
outside that, then
yes,
it will be a
that's
possible.
right. Yes, yeah. That's a problem. Yeah. Thank you.
Any other questions? Well, if not, we thank Dr. Baksalary for the very interesting talk.